we want to know what is the pH of a 0.3 molar hypochlorous acid solution. Okay, the Ka for hypochlorous acid is 3.5 times 10 to the negative 8th. All right, so for any problem like this where you are given a weak acid and you want to know about the pH, given its Ka, we can always write the equilibrium equation for the weak acid, right? So if you take that weak acid and you put it in water, okay, HClO plus H2O, and then that's in equilibrium with the proton transfers to the water, and you get H3O plus, a hydronium ion, plus hypochlorite ions. All right, and we have the given Ka. Okay, so we're starting out in order to find the pH, that's the negative log of the hydronium ion concentration. We need to find the equilibrium concentrations, and we know that the equilibrium constant is this. And so what we can do is an ICE table. Okay, ICE being the acronym for the initial, change, and equilibrium conditions. So we're starting out with 0.3 molar. That was given to us in the problem. We don't care about the water. We're not going to include that. It doesn't show up in our Ka, so we're not concerned about the liquid water. We don't have any ions to begin with. Okay, our initial conditions are just the 0.3 molar acid. All right, so now the change as we move from here to equilibrium, there's going to be a small shift toward the right. We obviously can't shift toward the left because we don't have anything here to remove. So there has to be a loss of reactants and a gain of the products. Okay, so and all the coefficients are 1, so those are just minus x and plus x. Okay, so at equilibrium we'll have 0.30 molar minus x for our acid concentration, and then x and x for the hydronium ion and the hypochlorite ion. Okay, so now we're going to put this in our expression for the Ka, and if we write that expression out, it's the product of the product concentrations divided by the product of the reactant concentrations. Okay, so here we're going to have H3O plus times ClO minus divided by, and again we don't put the water, so it'll just be the HClO. Right? Now I haven't explicitly shown it, but these three are all in aqueous solution, and then the water is liquid. Okay, so here we have our equation. We can put in the equilibrium concentrations from here, and what we'll end up with is x squared on top from the two concentrations here, each one being x, divided by the HClO's concentration, which is 0.3 minus x. Okay, so that's equal to 3.5 times 10 to the minus 8. Okay, so we could use the quadratic equation with this if we reformatted this in that form, but I think it's simpler. We can just assume that because this value is very small, we're going to have a very small number for x. Okay, and since that would be very small in comparison to this 0.3, we can assume that this difference, okay, if we remove just a tiny little bit from here, is not going to make any significant difference. Okay, so we can just ignore that. All right, and then now this becomes, we can reduce this down to x equals, it'll be 3.5 times 10 to the minus 8th times 0.3, so times 0.30, and then we're going to take the square root of that. Okay, so what we end up here with is we have 3.5 times 10 to the minus 8th times 0.3, take the square root of that, and we have x equals 0.000102. Okay, that's giving more significant figures than I need, but that's fine. All right. Now we should always verify our assumption. 0.0001. You can see that's pretty much less. If we subtract that from 0.30, we'll end up with 0.29999. So it's not going to make a significant difference there. At two significant figures, it's still going to be 0.30. Okay. So this is our concentration of the hydronium ions as well as the hypochlorite ions. Right? So if we want the pH from this, we'll just take the negative log of this value, and I'm just going to write that as 1.02 times 10 to the minus 4th. And what we get here is it'll be about 3.99. Okay, so that is the pH, and that makes sense. Very slightly more than 1 times 10 to the minus 4th. So that should be around 4. Okay, so that's the pH of a 0.3 molar solution of hypochlorous acid.